acetal formation. Aldehydes, when you react with the alcohol molecules, you get first a hemiacetal, and then a hemiacetal molecule again reacts with another alcohol molecule, and you get an acetal. This is called an acetal here. You have two OR groups, two OR groups on the carbon, right? So basically one aldehyde molecule reacts with the two alcohol molecules. When it reacts with the one alcohol, you get a hemiacetal. If it reacts with another alcohol molecule, you get an acetal molecule. Let's take here an example of the benzaldehyde. If it reacts with ethanol, now two ethanol molecules, they will react with the one benzaldehyde molecule, and then you get a acetal here, right? Let's discuss now the mechanism of this particular reaction. How do you get this hemiacetal and then an acetal from an aldehyde? So overall, we say that one aldehyde molecule will react with the two alcohol molecules, right? Okay, it's going to react with the two alcohol molecules. Let's say this is the ROH here, right? And two alcohol molecules, what you will get? You will get, this reaction actually occurs in the acidic medium here. And then what you get? You get a acetal molecule, right? You get a RCOR, H, and an OR. This is what you call as an acetal. First you get a hemiacetal, and then the hemiacetal converts to the acetal molecule here. So let's now discuss the mechanism. How do you get this acetal molecule from the aldehyde and the alcohol molecule? So basically what happens here in this process, the one alcohol molecule reacts with the aldehyde. So this is actually a nucleophilic addition reaction. When you look at the mechanism, so what happens, one of the alcohol molecule, see ROH molecule, it has a lone pair of electrons, acts as a nucleophile. It attacks on the carbonyl carbon here. So then what you get, once it attacks here, okay, this electron pair shifts in this direction. Now this is an addition reaction, okay, so you get RH, oxygen with negative charge. Now this alcohol molecule attacks on the carbon, so it forms an OR group here. Okay, let's take this R1 as an R prime. This is from the aldehyde to differentiate it, right? So this is the alkyl from the aldehyde, and this is the alkyl group from the alcohol. Now alcohol molecule attacks on it, this one, and this oxygen has a electron pair and also a hydrogen, so it has a positive charge. Okay, and then what happens, this molecule here, oxygen with negative charge, it picks up a proton. First this hydroxide, this H positive will be lost. It will be lost as an H positive, and then you can add the same proton to this oxygen, right? Okay, so you get an R negative, COH, H, and this is our R group. So this is an hemiacetal molecule. Here what we find one alcohol molecule adds across a carbonyl group, right? CO group. The pi bond breaks, oxygen attacks on the carbon, hydrogen goes to the oxygen, so you get a hemiacetal, right? You get a hemiacetal. And now the second molecule of this alcohol will react again with it. So how you can replace this OH by the alcohol? Again, as I said, this reaction occurs in the acidic medium. So basically in the acidic medium, this OH group over here is now protonated first. Okay, it forms a bond, so you get a molecule like this, or OH. This is a hydrogen, this is an OR here. The hydroxide now reacts with the proton, acidic proton, and it forms a bond with this, and this is now an oxygen with a positive charge. And then what happens, this electron pair shifts with the electrons with the oxygen, so there is loss of water, H2O molecule, and now you get a carbon with a positive charge. So you get intermediate like this. You got an R, C positive, H, oxygen, and it has an alkyl group also. Now this one can undergo the resonance, and it has, now there are two resonating structures for this intermediate. A carbocation is formed first, and then this carbocation can undergo the resonance because there is an oxygen with a lone pair of electrons. So now we have a positive charge on the oxygen. Now basically these are the two resonating structures, right, of this intermediate. And then what happens now, it is the alcohol molecule now that will attack on the carbonyl carbon, right? On this carbocation actually. Okay, so now the carbocation has been formed, and another alcohol molecule ROH molecule, it's gonna attack on this carbon. It will shift like this, and it will form an intermediate and something like this. Attach carbon with the hydrogen. There's an OR group now, and there is oxygen attached with the alkyl, and it also has a hydrogen, right? This one now, and this has a positive charge. And now what will happen? Again, this hydrogen will be lost as H positive, and then what you get? You get a carbon with alkyl group, hydrogen, OR, and now this is another OR. This is what you call as an acetal, right? Carbon with two OR groups. This is what we call as an acetal. So basically what happens in this whole process, first one alcohol molecule adds across a double bond, and you get a hemiacetal, and then again another molecule now replacing the OH group, correct? From the hemiacetal here, you can say this is a kind of a nucleophilic substitution. You are replacing this OH group by the OR group, right? So you get a acetal molecule over here, correct? This is how you get an acetal molecule from the aldehydes. Now ketones, actually, ketones, the difference is that ketones are less reactive than the aldehydes. Aldehydes are more reactive. Then what about the ketones? Can they form the, generally, the ketones have a lesser tendency to form the these acetals with the monohydric alcohols, right? So they have very less tendency to react with the monohydric alcohols. However, ketones can react with the diols. If you have a dihydric alcohols, right? You have a carbon like this, CH2 group, and it has a oxygen OH here. So now ketones, basically they actually react with dihydric alcohols, and they produce their a cyclic ketal, right? They produce a cyclic ketal like this. This when you react to this ketone with the dihydric alcohol, so H here, and oxygen from here you can replace, and then you can say you got a molecule something like this, R and R. Now you got oxygen, OCH2, and CH2, oxygen. The mechanism is again the similar to what we find for the acetal, right? First, the one of the OH group will attack on it, and then there will be a replacement of this OH group by the another hydroxide from the same molecule, and you get a cyclic ketal here, right? Okay, you get a cyclic ketal here. This is what we call as a cyclic ketal. Now these cyclic ketals and the even the acetal, they can be decomposed by the dilute acids. You can hydrolyze them, and you can get back the ketones and the alcohols, aldehydes and alcohols, right? So that's why we use this acetal formation as a a method to protect our groups in the organic synthesis. Suppose we have this molecule, and from this molecule you want to basically convert it into a substituted group. You want to replace this hydrogen by the methyl. So if you want to convert it into a molecule like this, CH3, C double bond O, CH2, carbon with triple bond, and you want to attach here, rather than hydrogen, right, you want to attach a methyl group, right? So if you have, this is your target, you want to synthesize from this molecule this one. Now what you can do, it looks like that you can take a methyl iodide, right? Normally, whenever you have to replace this hydrogen, acidic hydrogen, by a methyl, you can take the methyl iodide in the basic medium, correct? In the basic medium, this methyl acts as a nucleophile, it attacks the hydrogen as an H positive. So you can expect it like that, correct? You can expect this product will be formed here. But the thing is, if you do it, in the direct process, you won't get this product, right? You will not get this product because there is a carbonyl group in the same molecule, and we know that in the basic medium, carbonyl group is not like that. It will react with the hydroxide groups, right? With the hydroxide group. So that means this direct method won't work. This is not the best method to prepare this compound. You won't get this product here from this reactant directly reacting with the methyl iodide. Therefore what we should do, we have to first of all convert this carbonyl group here over into the ketals, right? You have to convert it into ketals, you have to protect it, you have to make it less reactive, and then after that you can replace this hydrogen. So the strategy is what? The strategy should be that we should protect this carbonyl group here. Okay, we have to react with an alcohol molecule so that it can form a ketal molecule, right? So that after that after it forms a ketal, then you can replace this hydrogen by a methyl. All right, so that means we have to first protect the carbonyl group, right? After the production of the carbonyl group, by forming what? By forming this ketal here, right? Then you can replace the hydrogen from this one by methyl. So that means if I want to convert it into the the final desired product, I have to first react this molecule with the diols, right? Because we know this is a ketone and ketones react with the diol. So this is a diol, and now you will get a cyclic ketal here. And now after that, in the basic medium, what you will get, in the basic medium, this is acidic proton, right? This is an acidic, and it's going to react with the NH2, and now you get a carbene in here, right? You get a carbon with a negative charge. You will get a carbon with negative charge. Now you can basically react this molecule with the methyl iodide. Now it is very easy to react with the methyl iodide, because from the methyl iodide this methyl can react with this one. Okay, this is the CH3I. It can react with this one, and what you get the CH3 product attached with the carbon. So directly you cannot do it, right? Directly you cannot do it. It's not wise to directly react with the methyl iodide before you do the production, correct? So that's why this acetal or the ketal formation is very good in the organic synthesis, because we use it as a protection a technique in most of the organic reactions. And then after you have protected this group, you can now deprotect it, right? Means you can replace this diol from it by the hydrolysis, right? If you do the hydrolysis now, you will break this molecule and you will get a diol back, and you will get C double bond over here. So if you do the hydrolysis, then what you will get the CH3 C double bond O, then CH2 carbon with triple bond, and then the CH3 here. All right, and this one will be converted into once you break it here and here by the addition of water, you will get another molecule which is CH2OH and CH2OH. You got this product back. Okay, this is ethylene glycol. You got it back. This one by decomposing this acetal with hydrolysis, acidic hydrolysis. Hope you got it. Thanks for watching the video. Bye for now.